has the hole in it. Just can't remember off the top of my head mathematically how to make it so it's got that hole in it.
Isn't it like a washer?
Why don't you, instead of using a equal sign, use an inequality?
Oh, well, then you get it shaded inside or outside, right? Then you get a shaded region. Then you get a solid, right? So once you get a surface, if you get a, like the M&M surface.
What if you limit the domain?
Then if I take its equation and put a less than or equal to, then I've got it filled in. I put the chocolate in there, right? Sound a little strange, but it's all right. So I wanted to show you some better images to work with. This one, unfortunately, has no equation to go along with it. But let's figure out what its name would be. Oh, yeah.
I think x squared plus y squared plus c would give us.
So why do you say that?
Because if we...
You're close, by the way.
Huh?
You're really close. The reason that the z variable is not the one that's squared, what kind of tells you that in this picture?
It's not radial. It's
not
like
it doesn't come back on itself in that direction, right? It doesn't complete it. It's not a loop. So if I want to make a sphere, then they'd all have to be x squared plus y squared plus, they all have to be squared. Because then it's not, would you call it, do you think this one, just to get ahead of myself, do you think this is a function? Do you think this represents a function? Let me give you an easy answer.
Yes.
And why? Like this one, is this a function?
No.
This is an obvious no. Right? Because thankfully our definition of function is the same for basically any dimension. Our definition of function says for any input there could only be one output. Right? That's why I always tell my students a lot like Highlander, if you ever saw that. Before they got all really freaky in part 2. And what I sort of hinted at before, and actually I might as well do this right now because this kind of feeds into this whole thing. Our inputs are now going to be what types of things? So, no. Never seen. So if I have something like this, is equal x squared plus y squared minus 2. So this is a good example of my xy trace would be what type of thing? XY trace. It would be a circle, right? Because for an xy trace, what do I make equal to 0? Z. And then I bring the 2 over, I get a nice little circle, a radius, square root of the 2. You with me? So my point is, we're talking about what makes a function, and I want to first start off with what are my inputs for this. So this is actually, I can replace z with f of xy. You with me? And of course I can do that here because z is not squared. The minute that all my variables are squared, does that represent a function? Hell no, because then it doesn't pass the good old vertical line test. What we're missing right now is that feel for, in 2D it's easy. I draw a vertical line through my input axis, right? That's what vertical is defined as, perpendicular to the input axis. What the hell is my input axis for this thing? Is it an input axis?
It's an input circle.
It's an input plane. In fact, specifically it's the xy plane, right? Or at least points out of there, because there could be, in this case, I can put whatever the hell I want to in there, right? Can I? Can I put x equal to 8 billion?
Yes.
Right? And then y equal to whatever. So I can put whatever I want to in there. And of course you see that because of what was being said earlier. My xy trace, all the traces parallel to my xy plane, they're going to look like circles. Right? And my z-axis, what is my xz trace going to look like, for example? Yeah, it's going to be z equal to x squared minus 2, and then z equal to y squared minus 2, just to get to the chase for my yz. So there's going to be open-ended parabola. So of course that has, as outputs, that has all z's, right? So that's why I'm allowed to input really anything I want to. There's no, it doesn't have to come back on itself. for example. The point I want to make right now is my domain is no longer just scalar. And it's not vector, it's my domain is a plane. My domain is now, or a subset of a plane. You with me? So in this case, my domain is the entire XY plane. Right? Now I could have, the reason I brought this here today was because I was frantically searching my office because I decided to do this at the last minute, and I was hoping I could find something like, I should have brought in a cut-off clear soda bottle so you guys could see through this damn thing. Because, for example, if I have my XY plane here, then the inputs would have to be like this. You with me? Because otherwise, every point has to have someplace to go. Now, what is my domain really, though? What about in the middle? Pretend like this isn't here. This metal part. You with me? So my surface is this, the wood. So right in the middle is going to be, I don't know, I'll just eyeball it. Wow. Those don't go anywhere. So my domain is this donut. My domain are all the XY points such that, let me see if I can make this make sense. XY, what's that have to be? X squared plus Y squared, less or equal to, let's say, 2, but greater or equal to 1. Is that cool? So it's in between those two circles. The point to make here is we're transitioning from my inputs being one-dimensional to my inputs being 2. And of course they have to be because now I've got 2 independent variables. So they're going to come from a plane. So at this point here, its output is right there. And so forth. So you can see, if I move in this direction just to look forward, what am I doing on my surface? Am I going up or down? Up. If I move in that direction, I am going up on my surface. So do you see how derivatives are eventually going to be a little interesting? Because they're going to be based on which direction I'm going in, right? Because if I go in that same direction, but here, am I going up or down? Down. Okay. It's a little preview, but the idea is pretty simple. You just have to look at your outputs and see what they're doing as you march around. But you have to, what happens in this class is, we talk a lot about 2D stuff, because a lot of what we talk about is based purely on the inputs. And our output is sort of like we're trying to maximize our output or minimize it or seeing how much our output changes, but we're focusing all our attention on just the inputs. Which is nice for us because the inputs are easy to graph because they're 2D for us in this class, right? Later they could be 80D. Not very easy to 80D. 70, 90. Let me make it so easy to do. You guys with me the whole thing? So now, if I ask you, is this a function? Does this represent a function? Because it passes the vertical line test. Vertical to the XY axis. So perpendicular to the XY axis. Any line I draw through will only go at most once through this. Right? Yes. Same definition, if you remember, from a million years ago. Right? That's the definition of function. Cool. So that is obviously not a function. This is actually, and you're used to, how do I?
But if you cut it in half, it's going to be a function, right?
There we go. And we'll talk a little bit about the names. Every single trace up here is itself what?
An ellipse.
An ellipse. So that's an ellipse. That's an ellipse. That's an ellipse. And of course, if you set, that's pretty easy to see mathematically.
Yeah.
Makes easy. That's an ellipse, that's an ellipse, that's an ellipse. And on isometric paper, that'll be damn easy to graph, right? You just have to find your 3 and 4, right? For the x and the y, 3 and 4, negative 3, negative 4, easy. They'll go to the other one, and then kind of connect those. You with me? The name is ellipsoid because all the traces are ellipses. Go back to this. Do they have the name on here? No. What do you think we'd call this? And this is why you were close with This is the equation that would give me circular traces. How would I make it give me elliptical traces?
You have denominators. Oh, coefficients.
Different coefficients,
So
right?
parabola is
So the main thing that this is, what's two of the traces in this are what shape?
still right. Parabola.
So that's going to be a paraboloid, specifically an elliptical paraboloid. Because the ellipse kind of forms my parabolas, how wide they get. They're controlled by the ellipse. You with me? So the shape that shows up the most is the oid part. And the shape that kind of is what those come together as is the adjective part. You with me?
Mm-hmm.
Okay. So if you look on page, for example, just to look ahead a little bit. Oh, where was this? Is it back here? Here, page 785. Let me see if I can pull it up here. I think I can. Ooh. 785. Let's see if we can pull it up on this guy. Here we go. Cool, I can. And I could probably move them a little bit. Little tiny ones. You see that? Yay. Look here. Elliptic paraboloid. Two traces are parabolas. One is ellipse. So it's elliptic paraboloid. Hyperboloid. Two traces are hyperbolas. Now this one is, we don't give it a nice little adjective, but one trace would be, actually they tell you, an ellipse, right? So if I made the xy trace, that's elliptical. But they decided to call it just a hyperboloid on one sheet versus two sheets, because that's the important step. We could call this an elliptic hyperboloid. I don't see why not. What would make it a circular hyperboloid? If A and B were the same. Cool? So I like that general idea. That's what governs this kind of name. The adjective is the one trace, and the oid piece is the one that shows up twice. You with me? So that's why this is elliptic parabola. You can see why they call it one sheet and two. Oh, here's some more stuff. Cool. Stay with me now. So here's one sheet because it's done in one sheet, and this takes two. So you can see kind of a limiting process here possibly, right? So if you look at the definitions, and actually look at the placement of the negative signs, this might tell you why one is this way and the other is the other way, right? But the naming, of course, makes sense. One sheet and it's done, but this one takes two. Okay, cool. You're not necessarily going to have to memorize these because you'll know once you do the traces, you'll know what situation you're in. So you don't have to directly memorize these, but they very quickly come out when you start doing the traces, obviously. Yeah?
I'm sorry, going back to how you decide to redefine what a function is in a three. I'm sorry, right behind your head.
Oh, yeah.
Yeah, so for any z value, it only, or for any z plane, is that what you said? Is that the
The
new definition?
function definition doesn't change at all.
Right, okay,
For every input, there can only be one output.
right,
That definition holds here also.
okay,
When I draw my vertical lines, if I want to think about it visually,
yeah,
the vertical line test is drawn all vertical lines, vertical in this case being perpendicular to the input plane. You guys with me?
So the hyperboloids are not functions.
Yeah, hyperboloids are not, the elliptical cone is not, anything that has an upper and a lower hemisphere, basically. Right? So if I wanted to come up, if I wanted to graph, oh, this is, of course, the coolest one.
so if it only converges once, then it's going to be a function.
It's a saddle, exactly. Sorry, say again?
So if any shell or three-dimensional shape only converges once, it's always going to be a function. Only converges once, as opposed to twice.
Well, it's the same idea, it can't come back on itself. So you got to be careful about that because it doesn't have to converge at all, but it can come back on itself many times.
Yeah, okay.
Yeah, it looks like a, I'm thinking of a collage, whatever you call it. Yeah, the size would be defined as sine functions, possibly. Yeah, cool.
Did you say Kugelhausen?
Kugelhausen, yes. Isn't that the shape of the? I was thinking of it right there. But yeah, if I define the circles of varying sizes, I can connect those with sine waves, right? With me? So that would be an example of one that is certainly not a function because it's got here and here. You know, vertical line goes through more than once. You guys with me? Okay. Cool. So it's nice that the idea of function carries over. It's the same idea as in 2D. Oh, let me see. Oh, they have something cool here. Oh, this is a cylinder, by the way, real quick. You draw a trace. This is actually the way you do any of these traces. This is the XZ trace, right? This is the XZ trace. And this would be maybe parallel to the XY plane at y equal to whatever. Right? And then you can connect those, and they actually connect them many, many times. Pop. One more. There you go. It's difficult to see like that, but if I move it a little bit there, you can see the curve. And then you just give it a nice outline on the outside. There's a cylinder. That's how you can graph a cylinder. So it's really, the funny thing is, and then they shade it in. Yay. The funny thing is, it's the same way we do any surface. For a general surface, I need a lot more than just one. Well, I need two more than just one trace. I need all three. This one's simpler because it actually just repeats that shape. For a general surface, I've got to get all the traces put together. Okay. This is not very interesting. Oh, one thing this does, I was supposed to do anyway. Oh, there we go. Okay. There we go. That's what I wanted to do. So this is an example of traces that are just parallel. So you can see the trace right at 5. It's just a point. Ooh, I think I went away from 5. Right at 5 it should be just a point, but it's giving me a little circle. And then of course it becomes a bigger circle, and then down to nothing. Cool. Or ellipse, sorry. I keep saying circle. This guy is the one that we're going to investigate. He's a really good example of the dangers you get into when you start trying to define derivatives. There's a point up here, the most interesting point up here. And this is a really good example also of, in one direction, doesn't this look a lot like that chute? Remember the chute we were talking about earlier?
Yeah.
And it's getting wider according to this, right? So this is the hardest part to get across on paper or to think about ahead of time, is how each direction, even though they could be parabolic in one direction, circular in another direction, they each have to kind of match up with the other. It's parabolic, but those are all just the circular edges getting bigger and it's making a parabola on the outside edge. That's the idea. I think somebody asked a question about that earlier. This point, obviously right in the middle, is a freaky point, and not surprisingly, we call that, this is just one example, but it's the reason we call it is that we call that a saddle point. Because if I move in this direction with my inputs, what happens to my z? Goes down. So in this direction, the derivative is negative. But in this direction, the derivative, it's hard to see on this, but you can see it's curving up, right? It's positive. So that point is a specific example of the general idea of a saddle point. It's like a place where well, it doesn't exist in 2D, but in 3D it's a place where the derivative is dependent on which direction you're looking, which isn't always true. Yeah.
At that point, isn't it 0?
At the point itself,
Yes.
It gets a little weird because it's supposed to be a derivative at a point. It's dependent on what's happening in the next step.
Yeah. So.
Right?
Well, yeah, I get what you're saying. I was saying the very that point.
Right at that point. Yeah.
Right at that point.
Let me see. Let me see if I can get it. I just can't get it any better. Oh, well, that's not too bad. So when you look at it this way, you can see very well the parabola here. Yeah. And this way, you can see obviously very well the parabola there. Yeah. Cool. Okay, that's pretty good there.
So what are we gonna do with those? What are we gonna do with those? Like, then we're gonna find volumes as well, or it's gonna be derivatives of those, or how are we like?
I use it. I want you to understand, we truly have, and I wasn't being, I think I said this the first day or very early on. When we learned vectors, we were as if we were beginning math over again, because you first learn numbers, and then you learn how to add them, and then you learn how to multiply them. We first learned vectors, then we had to learn how to add them, then we learned how to multiply them. Now we're up to the point of graphing, right? So it's sort of like, now we're just learning how to graph them. You know, and then that's sort of like Algebra 2 and into pre-calculus. Pre-calculus is what I call graphing hell, where you just graph the hell out of everything. You learn all these weird-ass theorems that tell you how many zeros and all this kind of crap. Right, so you make it through there. And then you get into calculus, so that's going to be the next step. So right now we're just talking about how to graph surfaces and what they even mean. I mean, how they come about. What am I allowed to plug in? You know, that kind of thing. Then we're going to talk about calculus ideas on top of this. So we really are sort of retracing, you know, our steps. We started at the basic Math 80 level of vectors, and then we're working up through everything all the way back up to calculus with this 3D stuff. Okay. So that's why I'm trying to give us a little preview of 3D derivatives are going to be direction driven. With me. So if I'm on a spot, and this is why I was showing that particular spot, but let me pick another one even.
Acceleration, velocity.
Let me see if I can do this. There. All right. So if I'm on that green circle, and I move in my XY plane, I move, my input moves this way. This is where it gets a little weird, but I think you guys were with me up here. It's the same idea. When I think about derivatives, I often think about, you know, in 2D, we just had to think about, you know, if I move from here to here, we're trying to maybe hone in on this guy's, I went up, so that derivative is going to be positive, that kind of idea, right? So the same idea here, but it's going to be totally based now on which direction. Here there were fewer options. Here there are more options. So if I'm facing that way and I go in that direction, I'm going to go.
Yeah, negative.
Now you got to be careful because it's actually sloping up here, right? So if my XY inputs move this way, I'm going to move that way. So I'm going up. So my derivative in that direction is positive. Whereas if I'm at the same point and I'm facing the other way, I'm going to go down. My Z outputs are going to get smaller. So that's where we're headed. We're headed into these things called directional derivatives, because it's all about what direction are you going to go in that's going to determine what your derivative actually is. So that saddle point, if you go one way, it's positive. If you go the other way, it's negative, right? Okay. Yeah.
For some of these cylinders, is it easy to deal with if we thought about a line or a curve rotating about an axis?
No, because a cylinder could be, you know, like here's a cylinder.
Yeah, I mean for some of them.
So there's a cylinder. I'm not sure. There's no rotation about an axis here, right? Is there?
No.
So thankfully, I'm sure none of us want to revisit this. Even though personally, once you teach it, you really, really understand. But you remember the whole thing about rotating it, and then you had to figure out, do I want to use a washer or a disc? Remember those days? Mm-hmm. And then you had radii involved, and you had to
People didn't like
do a
that.
subtract or add. Believe it or not, people don't like that in general.
It was easier.
That's not going to come into play here. Yeah, there's a few hurdles to get over conceptually to really see what the hell it's trying to do. And actually, what I finally, a student of mine gave me these. Remember, have you ever guys had these cheesy decorations where it's flat and then you open it up and it opens up? You know what I'm talking about? So that's a beautiful example of here's what it is in a plane, and then you rotate it around, and that's how you get this shape. I really like that visual, right? That's not really going to come into play here.
Why do we call this a cylinder?
Because the cylinder that we think of in everyday life is a specific example. That's a curve that happens to come back when it's up.
Okay.
So we do have, of course, elliptical cylinders. I think lathes nowadays, don't they come into those cylinders now that are elliptical? Sprinkles, of course, are the circular. Then you have the elliptical. We even have cylinders that go at a slant. Our cylinder is closed. That's a specific type of cylinder. Yeah. In mathematics, this is a cylinder, officially. Because it's a repeated shape. It's sort of like a prism is a repeated shape. This is a repeated curve. Yeah.
Sorry, going back to your bowl definition of a function, you said as long as the plane or the z value is drawn, for one input you're only going to get one output. But if you have an xy plane, then you're going to produce an ellipse or a circle, and that would not be a function, correct?
I didn't follow you. Sorry.
Just going back to how you defined a function versus three-dimensional shapes. You said as long as you drew a vertical plane, a vertical value.
Vertical line to the
Right.
XY plane.
Yes, like a trace. However, if it was xy through your bowl, you're going to produce.
Oh, no, be careful. In 2D, the vertical line test is a vertical line. How do you define vertical? You define it as being perpendicular to the x-axis, right? Horizontal line test is actually sort of an admission that it doesn't have to be this way. It could be that way. As long as it's perpendicular to whatever axis I want to think of at the time. So now, vertical line test in 3D means perpendicular to the XY plane. And in fact, it just has to be perpendicular to your input plane. Does my input plane have to be the XY plane? Hell no. Right? I think all of these are around the z-axis, unfortunately, but I could very easily put an x here instead of a z. And a z there instead of an x? Is there one that's
on page 787, there's one that's extruded across the x.
Oh yeah, they do have some in the book. I was hoping I could get one up here. Oh yeah, well they have page 779. They have some that don't go around the z-axis. Right, they could open up around the x-axis, open up around the y-axis. Yes.
You could do an example on the book, how to graph one.
Okay. Which one are you looking at?
About 46.
Whoa. 46 says this here. So there's going to be how many ellipses?
1.
And how many hyperbolas? 2. Alright, so this is going to be a hyperboloid of something. We could actually call it an elliptical hyperboloid if we really felt like it. My YZ trace is going to have what equation?
Y squared over 2, c squared over 36 equals 1.
No, they were a little bit evil here because if I want to graph this in my Y.
Oh, the square root of 2.
Yeah, they're a little evil, but oh well. Oop, my Z is going to be 6. Shoot, well, we'll just do this. Screw it, John, it's alright. So, again, so is everybody cool with this? I mean, the first 3 steps of graphing this is going to be easy. You're going to have 3 two-dimensional graphs to make.
When you combine them.
And then you combine them, that will be the hard part,
Yeah.
right? Obviously, I'm not trying to hide that fact from you. That will be difficult. So here, in the y direction, how far should it go?
That's it.
Yeah, root 2, so it should be about right here. Yeah, right, root 2?
Yeah. That's what's up.
So right there. And about right 1.4 there. And the z direction is going to go 6. So there's my ellipse. Now if you wanted to, at the same time, what happens if I make, now this would be x equal to 0, cool? This is x equal to 0. If I wanted to, I could look at, for example, x equal to whatever the hell else I want to make it. So if I make it x equal to 2, sure, what happens?
Instead of 9.
Yeah, 2 will be 4, 16, so it'll be 17. And why is that something that I don't really look forward to necessarily? The main thing to realize is, notice what's happening as you move away from the YZ plane. What's definitely going to happen? What am I going to have to do to this before I can graph this ellipse? Make it equal to 1. So divide by 17, which automatically makes my semi-major and semi-minor axes become larger. Right? That's the main point to make. It's going to be a bigger ellipse. You guys with me? Now, even just doing that, we've only done 1 trace so far. But as I move away from the YZ plane, as my x changes, what's going to happen to my my shape? It's going to be a larger ellipse. And if I go back to -2, the same damn thing, because x is being squared. So this is the skinniest it's going to be. And then it gets fatter ellipse this way and a fatter ellipse back. So I've done a lot of realizing about what this is going to look like already by just doing 1 trace and then 1 little parallel trace. You with me? I don't have to know what these numbers really are, and I don't want to. It's not that bad. It's just whatever square root crap, right? But the main idea here is it's going to be a bigger ellipse. Everybody see why? You guys cool with that? Because I have to divide by 17, making these numbers bigger, which makes how far I go out bigger. Okay. So what about the XZ trace? So what shape is that now? Hyperbola. And now you can kind of even start. Now this is admittedly.
That's a y square.
Where am I at? But for the XZ trace, what do you? Yeah, that's right. That's right. But see, those are the little things that are going to become second nature, sort of like finding intercepts. That is what we're doing, by the way, right? We're finding intercepts with planes. So anytime I want to find any intercept, something must become 0, right? 3 variables. I want to intercept with a plane, so I make one of them 0, so I'm left with 2 variables for that plane. This is a hyperbola. Now this is, of course, where some of you guys are going to have to go back to your how to graph a hyperbola, right? Which axis is this hyperbola going to sit on? Which one is it not going to touch, and which one is it going to sit on? Now remember, I'm talking about x and z, but I know what you mean. It's very simple to figure out. Can z be 0? Because then you're left with a negative squared equal 1. That can't happen, right? So if z can't be 0,
And it will never touch the z-axis.
They'll never touch z equals 0.
Touch the x-axis.
it'll never touch the x-axis, right? Because if it touches the x-axis, that's z equal to 0. You guys with me? Sort of, kind of? Okay.
I'm not sure.
No? Shit. You can even just start plugging points in, but can I plug in, for example, let me see. How far? I don't even know how far I want to go. I'll figure out the scale later. Z can't be 0, right? So I can't have any of these points, I can't touch the x-axis. So it's got to touch on the z. What's the smallest z can be? That would be when x is 0, right? You guys kind of with me here now?
Yeah.
Z can be bigger if x is not 0 because it's subtracting. So if I make x 0, what's the smallest z could be? 6 or -6, right? You guys with me? So therefore, that kind of gives you the idea of like closest approach here. I can get 6, and I can get -6, and then it's going to go out from there, right? If you want to do your little box and do your little asymptotes, or just get a couple more points and eyeball it in there, I don't need perfect sketches, but I need decent sketches for my traces, right? So just to get to the point, it should look like that, roughly. I don't know how fat or skinny. You with me so far? And of course, what's the XY trace going to look like? Much the same. And again, the same idea, which axis can it not touch? Because it's the same situation then. It's going to be, the formula is going to be y squared over 2 minus 4x squared equals 1. Make that a 1/4 if you go into do your A-B business. So it can't touch the x-axis, so the largest y can be is √2. I'm sorry. The smallest it could be is √2, and then it's going to open from there. Oh crap, that's beautiful. It's going to be like that. I don't know how fat or skinny, but again, you guys can get that, right? Either remember doing the old box, the old get your, you know, I don't know which way your teachers a million years ago showed you this. A is √2, B is 1/2 plus or minus. You guys remember that? So it's sort of like an ellipse that doesn't have, that's missing that. An ellipse would have both of these points, and hyperbola is missing a pair. Sounds bad for that hyperbola. So it's missing the 1/2. So it's got the √2. So here's the 1/2. Right there's my little imaginary. So there's my little box. Are you guys kind of with me on this? I mean, this.
Yeah.
Remember this? And then here's your guiding. So it should be skinnier than what I've drawn. Do you remember that well enough to do that? And if you forgot it, you can look it back up and you'll understand it quickly because you've gone through it once already. But to me, that's the quick way to get it. You got me? I hate it always, depending on which book, it always told you A and B is one thing or the other. Screw all that shit. You've already drawn the square root of 2 there. It must be the other dude that goes here. Connect those, there's your box. Diagonal is your asymptotes. Plop. Done. Right? Yeah.
So if this were on test, we could just do those,
Hell yes.
those 3 traces, because you keep on saying, well, then you have to connect, and that's going to get messy. That's what my question is. Could we just do exactly what you have there on the board, and that would be sufficient?
No, like I said, I'll tell you this. On the homework, no. On the homework, I am asking you to make an attempt at putting them together. On a test, I will give you the completed shape. Right? So which shape should this be? I think we already decided.
You said elliptical?
Hyperboloid. And in fact, you know it's going to be how many sheets? If it was 2 sheets, and I don't know if you guys were seeing this earlier. We go back. Oh shoot. Sorry, I know I'm talking about a lot today. Here's 1 sheet, here's 2. To be 2 sheets, what does the XY trace have to do?
You should have
The XY trace must not exist. Right? To be 2 sheets, the XY trace, and we can see it here. XY trace, negative stuff equals positive 1, don't exist. Right? So I already know it's definitely a hyperboloid of 1 sheet. And again, remember what was going on here? Ellipse, as I move away, gets bigger. On the other side, the same thing. As I move away, it gets bigger. Remember that? And how are the sides being governed? By that hyperboloid. So that's going to be like this. Here, as I move away, I think I had a better...
Except it's going to be the Z2X inside.
I had a better one here. Here we go. Perfect. This is basically the situation we're in.
Except the X will be inside.
Exactly. So In this case, see how the z is the one with the negative? Here the x is the one with the negative, so I know it's going to be this shape opening around the x-axis, right? Do you guys see that? This formula, the x is acting like it is in the z, as the z is in that formula, it's going to be opening on the x-axis then. And in a way that shouldn't bother us because they're just arbitrary choices for direction and notation. X, Y, Z, this way, who gives a shit? It's arbitrary. Yeah?
Yeah, so it seems how the coefficients and the denominators are different from yours. Does that mean you rotated?
Oh yeah, the width of it will be different. Right, because that's governed by the hyperbola and the edges of the ellipses.
Right. I was curious if you take the entire shape and rotate it 90 degrees.
Well, that's rotated because of the fact that it's around the x-axis, not the z-axis.
Okay.
So it would end up looking more like this for us. Let me see if I can make it. Oh, that's going to make me sick. Like that. Whereas z is more like our x. You guys with me?
Yeah.
So can you see how... Stop it. There we go. See in the middle? It's where it gets the skinniest.
Yeah.
And we saw that earlier, how you get further away, it gets fatter ellipse. And the edges of those ellipses come together to make those hyperbolas, right? You guys with me? And of course, somebody pointed out, there's more than just the stupid XZ trace and all that crap. You got these angular traces. They're all going to be also hyperbolas. But those are really difficult to get, so screw it. I'm just going to kind of fill it in. Knowing that my equation is decently symmetric in that rotation. I don't have to worry about getting those intermediate things. I can just fill it in. I don't have to worry about the rest of them. I just get the basics. Does that make you feel a little bit better about this? Okay, good. A little bit. Now the nice thing is, I don't know if this is a nice thing or not, but I've actually already sort of lectured over 12.2 also. Because 12.2 goes into domain, the definition of function. To me, that kind of all had to be discussed at the same time. So we've already sort of covered 12.2. There are a few things in 12.2 we still have to cover, so we're not quite done with it. Since I have talked so damn much today, I'm going to let you out a little bit early. Try to do what you can on this, and then first thing next time we'll do this. This is a quick quiz on section 12.1. If you have not yet found yourself isometric paper stuff online, come by and see me or ask somebody else who has. You definitely want it for this chapter. So the challenge is these knives. Sometimes. Nada? No. I didn't see them.
Okay.
Oh.
Joe.
You can get us plus 8. Well, you know, like I said over the email, we have a lot of